Hello students. In the previous lecture, we already started the introduction about signals and systems. We defined signals and we classified the signals into two continuous time signals and discrete time signal. The continuous time signal acts as a function of a continuous time variable t, and a discrete time signal acts as a function of integer n. And we defined the two parameters, signal energy and power, and we showed the two formulas to calculate the energy and the power. For example, for a continuous time case, we have to do this integration from minus t to t, the absolute value of x of t squared dt, and the power we have to divide the energy divided by 2 times t. And for the discrete time, we have the summation formula, which is summation from minus n to n, absolute value of x of n square, and for the power, we have to divide by the number of samples to get the power. Today, we will continue to discuss transformation of independent variables and some other concepts. One of the central concepts in signal analysis is to transformation of one signal to another signal. For example, of particular interest is transformation of the independent variable t. So t is transformed to alpha t plus beta. In other words, if I have a signal x of t, then if I want to find another signal y of t, which is equal to x is equal to alpha t plus beta, then how does it look like? Where alpha and beta are real numbers. Okay? If the absolute value of alpha is less than 1, then the signal will be stretched in time. That means, for example, if alpha is 0.5 here, then y of t will be, the duration of y of t will be twice of the duration of x of t. So it will be stretched. The signal will be stretched in time. If the absolute value of alpha is greater than 1, the signal will be compressed in time. And if alpha is less than 0, the signal will be time reversed. Okay, time reversed means reflection of the signal across y-axis. And if beta is negative, we have a delayed signal, and if beta is positive, we have advanced signal. Okay, it's better to see with examples here. For example, I have here a signal x of t from 0 to 2. From 0 to 1, it is 1, and between 1 and 2, I have here a decreasing slope. Okay, a decreasing slope. So we can see the additional lecture notes here. So I have here x of t is equal to 1 between 0 and 1, and it's decreasing and goes to 0 at 2, and it will be 0 for time t greater than 2. So I have this kind of shape, that means. So how do we get x of t plus 1? X of t plus 1 means shifting of the signal by 1 unit to the left. Beta is positive, so 0 will come to negative 1, and this 1 will go to 0, and this 2 will go to 1. So it's shifted in time by 1 unit. We call the signal is advanced in time because this signal occurs before this signal. This signal starts to be 1 at 0. This starts before that. It starts at negative 1 to be 1. So it is advanced in time. Okay, so we can find also the interval where it is different from 0. The original signal is different from 0 between 0 and 2. So the translated signal should be different from 0 between 0 and 2. 0 is less than t plus 1, less than 2. And if we subtract 1 from both sides, I have negative 1 less than t less than 1. So it will be between negative 1 and 1. So what about x of minus t plus 1? So I have t plus 1 already. Then I have minus t, means reflection across the y-axis, or the signal is reversed in time reversal. We call it time reversal. So that means consider the y-axis as your mirror and reflect the right side. Find the reflection of the right side, and the right side goes to the left side, and the left side goes to the right side. Okay, that is reversed. So the shape will be like this. Okay, the triangle part is to the left, and then the rectangle part is to the right. All right, so this is x of minus t plus. What about if I am looking for y of t x of 3 over 2 times t? If you see here, alpha is greater than 1. Okay, from the original definition, remember, t is becoming alpha t plus beta. Okay, for this example, beta is 0 and alpha is 3 over 2. If alpha is greater than 1, what will happen? Compression in time. Signal will be compressed in time. And if alpha less than 1, stretching in time. Okay, so here 3 over 2 is greater than 1, so the signal will be compressed in time. Here it was between 0 and 2, so every time in point, every point will be divided by 3 over 2. So 0 divided by 3 over 2, 0. 1 divided by 3 over 2, 2 over 3. 2 divided by 3 over 2 is 4 over 3. You see, so the signal will be between 0 and 4 over 3, compressed in time. Okay, again, we can check the interval where it is different from 0. X of t is different from 0, the original one, between 0 and 2. And the transformed one, 0 is less than 3 over 2, t less than 2. And if I divide by 3 over 2 everything, between 0 and 4 over 3, I will get. Now, if I have both scaling, we call also time scaling. Remember, compression and stretching, we call them time scaling. And if I have time shifting and time scaling, both 3 over 2 t plus 1. So I have time scaling by 3 over 2, time shifting by 1. So normally do the shift first. So x of t goes to x of t plus 1. X of t plus 1. Then you scale it by 3 over 2 to get x of 3 over 2 t plus 1. So x of t plus 1, we found it before. This is x of t plus 1. So then you scale this everything by 3 over 2. Negative 1 will be negative 2 over 3. 0 will be 0. 1 will be 2 over 3. So I have between negative 2 over 3 and 2 over 3. See? So this is the shifted and scaled signal, both. If I have x of 0.5 t minus 2, what should we do? First, from x of t, we go to x of t minus 1, minus 2, shifting by 2, to the right or to the left? To the right, of course, because minus. To the right means it will be a delayed signal. So 0 will go to 2, 1 will go to 3, and 2 will go to 4. So I have the signal starting from 2. It's delayed, you see, it's delayed in time. Then after you do the shifting, we scale it. Divide by each point by 0.5. If I divide each point by a small number, it means stretching. Divide by 0.5. 2 divided by 0.5, 4. 3 divided by 0.5, 6. 4 divided by 0.5, 8. So it will be between 4 and 8. Again, we can check the time interval where it is different from 0. So x of t different from 0, between 0 less than t less than 2, and x of 0.5 t minus 2 different from 0, between 0 less than 0.5 t minus 2 less than 2. And first add 2 on both sides, between 2 less than 0.5 t less than 4, and then divide by 0.5 between 4 and 8. So we get the final result, this one. Okay, so to summarize, when we do transformation, first we do the shifting and then the time scaling. And keep in mind, if beta is positive, then shift left. If beta is negative, shift right. If the absolute value of alpha greater than 1, compression in time. If the absolute value of alpha less than 1, stretching in time. And if alpha less than 0, flipping in time or time reversal. Okay, so that's all about transformation. Let's go to periodic signals. When we say a signal is periodic. Last time we saw an AC sinusoid signal, which is periodic, you remember, sine wave. In general, if I have a signal x of t is equal to x of t plus capital T, where capital T is greater than 0, means positive number, and this is true for all time t, for all small t, okay? For example, if small t is 0, x at 0 will be x at capital T. If small t is 1, x at 1 will be x at 1 plus t. If small t is 2, x at 2 will be x of 2 plus t, capital T, and so on. So if I have this, then we call capital T is the period of the signal. The period of the signal. Among the periods, I can have so many periods which satisfy this mathematical relationship. Among all the periods, all possible periods, the smallest period, capital T, the smallest capital T, we call it the fundamental period. Okay, we call it the fundamental period. So, for example, in general, if I have a sine signal, x of t is sine pi over 8 times t. For example, here pi over 8 is omega naught. So in general, a general sine signal, as we discussed in the previous lecture, is x of t, a sine omega naught t plus theta. Omega naught is the frequency in radians per second. Theta is called the phase angle. A is called the amplitude. Omega naught is 2 pi over t naught. T naught is the fundamental period. F naught is the fundamental frequency, 1 over t naught. The unit of F naught is hertz, or cycles per second. Now from this, if I compare this example with the general formula, omega naught is pi over 8, and my theta is equal to 0 because I don't have here theta. Okay, additional thing. So omega naught is pi over 8. Then how we determine the fundamental period? The fundamental period, we use this formula. T is 2 pi times m over omega naught, where m is integer. M is integer means positive integer means 1, 2, 3, and so on. Okay? So, of course, m is equal to 1. When m is equal to 1, we will get the fundamental period. So, for this example, what's omega naught pi over 8? So, 2 pi m over pi over 8. So, I have 16m. So, when m is 1, 2, 3, I have 16, 32, 48, 64. Note that all these are possible periods. So that means if I have 16 here, x of t for this signal is x of t plus 16. And x of t is equal to x of t plus 32. X of t is equal to x of t plus 48. All these are possible periods for x of t. Among that, the smallest one is 16. So the smallest one we call is the fundamental period. So T naught is equal to 16 is the fundamental period. So if I substitute 16 x of t plus 16, then let's do x of t plus 16. Instead of t, I substitute here t plus 16, then pi over 8 times pi over 8 times t times pi over 8 times 16. Pi over 8 times 16 is 2 pi. So I have sine of pi over 8 times t plus 2 pi, which is equal to sine of pi over 8t. Why? Because sine and cosine are periodic with 2 pi. Pi means 360 degrees. Remember this. So 16 is the fundamental period. Okay, if I have two signals with different frequency, how can we find the fundamental period? That means I have a signal which is a sum of two frequencies here. For example, x of t 0.5 sine pi over 8 times t plus 2 sine pi over 3 times t. So the first part is 0.5 sine pi over 8t, and the second part 2 sine pi over 3t. Then I will find the individual periods, and I select the smallest common for the two sets. Okay, so let's say for the first part t1, 2 pi m over omega 1, 2 pi m over pi over 8, 16m, m1 to 3. So it will be 16, 32, 48, 64, and so on. It will continue. And the second one, t2, 2 pi m over omega 2. What is omega 2? Pi over 3. Pi over is equal to 6m, so it will be 6, 12, 18, 24, and so on. So I have one set, which is this one, and another set, a set of possible periods, this one. So because the signal is the sum of the two, I should select the one which is the smallest common period. So the smallest common is 48. So 48 is the fundamental period of this signal. All right? T is equal to 48. If I have like this, if I have another one, this, okay, pi over 8t and pi over 4, again, for pi over 8, we have this one, the first one. And for pi over 4, I have 8m, 8, 16, 24, 32. Then the smallest common between this one and this one is 16. So 16 is a fundamental period. Okay. If I have this, in this case, pi over 8, pi over 4 is 2 times pi over 8. So in the to determine if I have one frequency a multiple of the other one, then choose the smallest frequency to find the period, the fundamental period. So the smallest frequency is pi over 8. Then 2 pi m over pi over 8 is 16m. So 16 is the fundamental period. Okay. So this is how we determine the fundamental period for a signal consisting of a sum of which is a sum of different frequencies. Okay, even and odd signals. Okay, so we did this. An even signal is identical to its time reversal signal. That means if I have x of t, then is equal to x of minus t. So what is x of minus t? We say time reversal or reflection across y-axis. Then we say the signal is even signal. For discrete, it is the same. X of n is equal to x of minus n. So for example, cosine. X of t cosine t. If you reflect cosine t, cos of t is equal to cos of minus t. So this is an even signal. X of t is equal to constant numbers. This is also an even signal. What about an odd signal? An odd signal is a signal where x of t is equal to negative of x of minus t. So I have time reversal and also the amplitude multiplied by -1. X of n is equal to x of minus n. So there is here a reflection on the x-axis, and there is a reflection across the y-axis and x-axis. Okay, so first we do across y-axis and then across x-axis. That means, so example, x of t is equal to sine t. So sine of minus t is equal to minus of sine t. So minus of sine of t is equal to minus of sine of minus t, and x of t is equal to t. These are odd functions. An important property for an odd signal is the value at 0 is equal to 0. X at 0 is equal to the value at 0. X at 0 is equal to minus of x at minus 0. Okay, how do we find the even end part of a signal? A signal can be pure even signal, pure odd signal, or it can have both even part and odd part. So what are the formulas used to find the even part and the odd part? We can find the even part of the signal is equal to 1 over 2 x of t plus x of minus t. So we have x of t and we have the time reversal signal x of minus t. We add the 2 and we divide by 2. We get the even part. And for discrete the same, only t change to n. The odd part x of t minus x of minus t divided by 2. For the even plus, for the odd minus. Let's have this example. This is discrete time signal. X of n is equal to 1 for n greater than or equal to 0, 0 for n less than 0. So it is 0, 0, 0, and starting from 0, it's 1, 1, 1. Let's find the even part and the odd part. Okay, let's find the even part and the odd part. So to find the even part, we use the formula. The even part is how 1 over 2 x of n plus x of minus n. So I have this x of n, and then what is x of minus n? Flip it. Flip this across the y-axis. So your y-axis is here, vertical. So when you flip, the right side goes to the left to the right. So I have 1, 1, 1, 1, 1, 1, and the 1 at 0 stays the same. And to the right, it will be 0, 0, 0, 0. This is x minus n. Now add these two and divide by 2, we get the even part. So when we add these two, here to the left of 0, this one is 0, and this one is 1, 1, 1, 1. So 1 plus 0, 1, 1, 1, 1, 1, divided by 2, it will become 0 0.5, 0 0.5, 0. At minus 1.5, at minus 2.5, at minus 3.5. At 0, this is 1, the time reversed 1. The original one is 1, 1 plus 1, 2 divided by 1, 1. Okay, the original for t greater than 0, it is 1, 1, 1, 1. The time reversed, it is 0, 0, 0. So add the 2, it will be 1, 1, 1, 1, 1. So at 1, 1, at 2, 1, at 3, 1, divided by 2, 0 0.5, 0 0.5, 0 0.5. So this is the even part. The odd part, instead of adding, we subtract. So this one minus this one divided by 2. Again, to the left of 0, I have 0, 0, 0 minus this one, 1, 1, 1, 1, 0 minus 1, it will be negative 1, divided by 2, it will be minus 0 0.5, minus 0 0.5, minus 0 0.5, and so on. At 0, the x of n is 1, x minus n is 1, 1 minus 1, 0. At 1 and greater than 1, this is 0. So this is 1, 1 minus 0. Okay, at 1 is 1 minus 0, 1. At 2, 1 minus 0, 1, and so on. Divided by 2, 0 0.5, 0 0.5, 0 0.5. Okay, this is the odd part. So to check when I add the even and the odd, I should get the original. So if I add these two, for the negative time, remember one of them is positive, the other is negative, they cancel, so it will be 0. At 0, this is 1, okay, and the even part is 1, so it will be 1, okay. The odd part is 0, so it will be 1. And at 1, this is 0 0.5. At 2, 0 0.5. This is 0 0.5, 0 0.5. If I add, I will get 1. So starting from 0, it will be 1, 1, 1, 1, which is the original signal. Okay, this is how we find the even and the odd part of a signal. These are important formulas. Okay, real and complex signals. Okay. A very important class of signals is continuous time signal of the form exponential form e to the power of st. S is a complex number, and discrete time signal of the form x of n z power of n, where z and s are complex numbers. All right. So if I have x of t, for example, if s is j pi over 8, j pi over 8, so x of t will be e to the power of j pi over pi t over 8. And using Euler formula, remember, if I have e to the power of j theta, what is the Euler formula? E to the power of j theta is cosine of theta plus j sine theta. So the real part of this is cosine of pi t over 8. And the imaginary part is sine of pi t over 8. And if I have discrete, similar, but the variable t changes to n. Okay, so this is a real part, real signal, and if I have everything, I have the complex signal, which has a real part and imaginary part. So if I plot the real part is like for the continuous time, I have cosine pi t over 8, like this. You can plot this, for example, in MATLAB as a function of time between minus 20 and 20, still like this. And remember what is fundamental period. Fundamental period, we said, is before we calculated 16. So after 16, it will repeat itself. That means, so for example, how we locate it in the graph, at t is equal to 0, here I have 1. Then I look the next peak. The next peak is at this point. At this point, at this point is the next peak, which is 16. So this is the fundamental period is 16, that means. And for the discrete time, the only difference is this is continuous, and the sampled value of this I will have like this. And again, the fundamental period here is 16. So at 0 it was 1, and then after that at 16 it starts to be 1. Okay, exponential and sinusoidal signals. We will see it in the next class. Okay, thank you for listening to this lecture.